Yes.
Yep. Everybody okay?
Perfect.
Yes.
Perfect. Yep.
Okay. All right. Welcome to course number 4 in the Optimising Pulley Lagging Performance series of webinars. Today's topic is, just hang on a sec. Today's topic is identifying potential for performance improvement. And in today's session, we'll look at ways of identifying opportunities for improved lagging performance on both new conveyors during the design stage and also on existing conveyors. By improved performance, I'm referring to improving the performance of the pulley lagging and conveyor belt interaction. To start with, let's look at drive pulleys on conveyors in the design stage. Here we'll be looking at things like power transfer, localized slippage, the inherent cyclic shear stresses that both the lagging and the belt splices have to deal with. We'll be looking also at how this relates to the fatigue life of each of these components. In course 2, we discussed using the Lagging Select software tool to identify lagging failure root causes and to assist in evaluating options for addressing these root causes. But there's another way that this engineering tool can be used, and that is to evaluate different lagging types and designs on drive pulleys by comparing a number of key performance criteria, specifically localized slippage, fatigue failure, in particular in 3 key areas of the lagging, actually 4 key areas of the lagging. You can see here we have the pulley shell interface, the tread root, which is at the base of the grooves on the lagging, the contact face, and the tile bond surface. Additionally, the tool allows us to look at the shear stresses that will be applied to the belt and the belt splices. And this can be important in maximizing the service life of both. What I want to do is just run through quickly a number of different lagging types. We'll look at a couple of rubber laggings and then a number of different ceramic pulley lagging options with different patterns. Different tile configurations and also different thicknesses. We'll look at the performance of each one, and then at the end we'll summarize and look at which is the best option. All of the following analyses have been done with the same conveyor data. Now, the data you can see is on this table on the left-hand side. We've discussed it in some of the previous courses. One of the interesting things with this set of data that we're going to use for comparing the different laggings is that the T1 to T2 ratio on this particular conveyor is quite high at 3.57. Having a higher T1 to T2 ratio results in greater retraction of the belt as it moves around the pulley. This is the first lagging. It's 12mm diamond rubber, and the analysis shows localized slippage. We can see here that the localized slippage starts at around 175 degrees around the arc of contact, and it results in a total of 37 degrees of slip, or 18% of the wrap angle. Down in the bottom of the table here, these results here, the contact face shear stress, the tread root shear stress, the pulley shell shear stress, and the tile bond shear stress. These are the fatigue results. So long as they're below 100%, it means that the lagging is capable of handling the 5-year service life that's built into the tool. And I want you just to keep an eye on these figures here, which we will discuss at the end when we do the summary. The first one is the minimum tension, T2 tension to avoid localized slip. And then the one below that is the maximum shear stress between the lagging and the belt. Okay, the next version is 25 mil diamond ceramic. In this case, the lagging's more flexible, and as a result, the localized slippage reduces to 19 degrees or 9% of the arc of contact, which is an improvement over the previous 12 mil. There's no fatigue problems. You can see that none of these figures down the bottom here are exceeding the 100%. Now we'll look at ceramic lagging, and the first option is 12 mil diamond ceramic lagging. This is essentially the same as the previous 12 mil diamond rubber lagging, but with a dimpled tile bonded to each of the large diamonds. The localized slippage is still present, but it's reduced. It's reduced to 14 degrees or 7% of the arc of contact. You can also see here that the fatigue life of the pulley shell lagging interface and the tile bond shear stress have exceeded the limit. That means that lagging would not be expected to last the 5 years service life. Now we'll go to a 25 mil version. Guys, can you put your audios on mute for me? There's some feedback noise coming through.
Let me try that.
Okay, now the 25 mil thick diamond ceramic, the localized shear, or sorry, the localized slippage has reduced. We only have 7 degrees, which is 3% of the arc of contact. The tread route has just gone over the fatigue limit for 5 years, so it's right on the borderline. Let's have a look at 20% ceramic lagging, 12 mil. We have 21 degrees of localized slip, which is 10% of the arc of contact, no fatigue problems. When we go to the 25 mil version, there's no theoretical localized slippage and no fatigue problems. So this is the first of the laggings that we've looked at where we have neither localized slip or any sort of fatigue problems. Interestingly, if you just look at these numbers here, the T2 tension to avoid localized slip is 90 kilonewtons, and the maximum shear stress is 86 kilopascals. When we get to the end and we do the summary, you'll see why that one's significant. So this is a common single row ceramic, 12 mil. We have 40 degrees of localized slip, which is 19% of the arc of contact. We have no fatigue problems. We'll go to the thicker version, which is 25 mil. The localized slippage is reduced to 21 degrees or 10% of the arc of contact. Again, no fatigue problems. The last lagging type that we'll look at is what's called 80% or full ceramic. You can see here we've got slippage starting at about 155 degrees. So we end up with 54 degrees of slip around the arc of contact, or 26%. No fatigue problems. And when we go to the 25 mil version, not surprisingly, the localized slip reduces to 33 degrees, 16% of the arc of contact. So that's all the different lagging types. Let's look at the summary. So what we've got here is the different lagging types that we just looked at across the top with their different ceramic levels of ceramic coverage. We've then got the traction. When you exceed 100% of the traction, that's when you've got slip. This is the amount of slip. Then these 4 lines here relate to the fatigue of the lagging. So we've got the contact face shear stress or fatigue. We've got the tread root, the pulley shell, the tile bond. So there's only one lagging that basically has no localized slippage and is well within the fatigue limits, and that's the 20% 25 mil lagging. And remember earlier on I mentioned about the minimum T2 to prevent slippage and the maximum shear stress. For this lagging, the minimum T2 to prevent slippage and the shear stress are the lowest for all of the laggings that we looked at. And that's important because you're putting the belt and the belt splices under less stress. So what this analysis is enabling us to do is to select a lagging that is not at risk of having localized slip. It's also within the fatigue limits, so we can be confident that we won't get fatigue failure within the 5-year limit in the tool. Then at the same time, the lagging belt interaction is operating at lower levels of tension and stress. Let's have a look at non-drive pulleys, again for new conveyors. Often decisions on new conveyors are driven by a desire to keep the capex to a minimum, and this can be done at the expense of higher operating expense once the conveyor is running. The following discussion is based solely around the best operating performance, and I'm not considering the upfront capital cost. So for non-drive pulleys, there are 2 main considerations for lagging performance and service life. The first is resistance to wear. And these photos show some examples of wear on non-drive pulleys. More often than not, the wear on the non-drive pulleys is localized rather than uniform across the pulley. And this is often due to localized shear forces on the pulleys due to factors such as short belt transitions, turnover conveyors, uneven belt stretch and recovery with things like PVC solid woven belt. The photos on the left-hand side and the center are on a conveyor with a turnover belt, and the photos on the right-hand side are from contact with a PVC solid woven belt. The second criteria for lagging performance on non-drive pulleys is resistance to build-up. And this is particularly important for pulleys that are contacting the dirty side of the belt. These photos show several pulleys all contacting the dirty side of the belt and having to deal with the challenge of build-up. Photo on the right, it's pretty tough operating conditions. Let's first of all look at resistance to wear. And to understand this, I just want to talk about how we measure the wear on different types of lagging. Most readily used test method for evaluating resistance to wear or abrasion is called the rotating drum abrasion test. The basic test machine is shown in this photo. It consists of a rotating drum that is covered with abrasive paper, and a sample of the material being tested is weighed before and after testing. The test being that the sample's held onto that rotating drum with a known force while the drum goes through 80 revolutions. And the material loss is measured as the change in weight, and which then can converted to a volume loss. Now, the important thing is that the lower the test result, so the lower the volume result, or the lower the volume loss, the greater the resistance of the material to wear and abrasion. So a lower figure means better. When we look at the second important criteria for lagging on non-drive pulleys, resistance to build-up, there are two physical properties that have a direct impact on this: flexibility and low surface energy. Flexibility allows the material to resist sticking by moving and flexing under load. It effectively prevents the material from attaching to a fixed static surface. Low surface energy is indicative of materials that are difficult to stick to. Probably the most common material that you would know is Teflon or PTFE, although we don't use that in pulley lagging. Of the common lagging materials, the one that has the lowest surface energy is polyurethane. At Elastic, we have used polyurethane on a number of non-drive pulleys where there's been localized wear showing in rubber lagging. And just the change to PU lagging has greatly reduced this. And that's due to a combination of the low surface energy and the improved abrasion resistance. This table provides a comparison of the most commonly used lagging for non-drive pulleys. And with regard to abrasion resistance, so we look at across the top here, this is the volume loss. This column, plain direct bond ceramic, or this is true for any type of ceramic, very low abrasion loss. You know, ceramic is by far and away the most abrasion resistant material. So for non-drive pulleys that are contacting the clean side of the belt, where carryback and build-up are not a problem, ceramic lagging will give you the longest service life. The next best for abrasion resistance are polyurethane and extreme rubber lagging, both with abrasion loss of below 30. And if you compare that, like a really good quality rubber lagging would be less than 90. An M grade conveyor belt is less than 130. We talked about flexibility before, so hardness. The most flexible laggings are rubber, standard rubber or extreme rubber, and then polyurethane. Polyurethane is more flexible than ceramic. If we then look at the different laggings in relation to surface energy, polyurethane has the lowest, ceramic the highest. For the clean side of the belt, ceramic would be expected to give you the longest service life, standard rubber the shortest, and for the dirty side of the belt, polyurethane and extreme rubber would be the best. And direct bond, problem with direct bond is that it can be prone to build up, and when you get build up on ceramic lagging, it puts high shear stresses onto the belt and the belt splices. One other consideration is the protection of the shell from corrosion. In these examples, I've only considered hot vulcanized polyurethane or hot vulcanized rubber lagging. And hot vulcanized lagging or direct bond ceramic all protect the pulley shell from corrosion, that there's no joints to open up, the edges don't lift. So that's a way of getting maximum service life. So what does this mean for lagging selection on non-drive pulleys? The clean side of the belt with no build-up, ceramic lagging is the best option. Dirty side of the belt, extreme rubber lagging or PU Typically changing from standard rubber lagging to polyurethane or extreme rubber lagging, you'd expect to increase the service life by 3 to 5 times. So let's have a quick look at how we can improve performance on existing conveyors. And when we look at existing conveyors, there's one question that we ask. That's basically, is the pulley lagging lasting as long as the bearings and the locking elements? Pretty much in every application, with the exception of high tension bend pulleys, it's possible to have lagging that should last as long as the bearings and the locking elements. First thing that we'll look at, or the first mode of failure we'll look at, is debonding of lagging, and I'm going to lump in edge lifting and joint separation. The pulley on the right hand side has been operating in a very wet environment in an underground coal mine and has severe edge lifting and joint separation. But if you actually look at the lagging itself here, the lagging's in really good condition. It's just that it's separating, and in this case it was coal bond lagging. These other two are drive pulleys, also with coal bond lagging. Problem of debonding and edge lifting joint separation is a pretty easy fix by changing to hot vulcanized lagging or direct bond lagging. You can pretty much eliminate these problems. The second failure mode we'll look at is tire loss. The two main causes of tire loss. This photo on the left is an example of failure of the bonding system, and this photo on the right is tire loss due to operational conditions, where the tiles have physically been torn out of the rubber backing, as opposed to the bonding system failure, where you can see these neat little pockets. Let's first of all talk about bonding system failure. Basically, it's a manufacturing fault, and there's a whole range of different causes, different things that can cause it, but it is predominantly a manufacturing fault. It's the most common form of ceramic tile loss or ceramic lagging failure. Things that you can do to overcome this is basically evaluate the lagging manufacturer's track record with regard to tile loss problems, and then find out what sort of warranty is provided against tile loss. When ceramic lagging is being manufactured correctly, the tiles should not fall out of the lagging for the life of the pulley, unless there's some very unusual operating conditions, such as high temperature or really high cyclic shear stresses. Tile loss due to operational conditions, such as high shear, results in the tiles being torn from the rubber backing, and you get a jagged rubber pocket where the tile was, and typically the tiles will come out with rubber attached to them. This is most commonly seen on high tension bend pulleys, which is the photo you can see here in the center. Here, the high localized shear forces due to the belt cover wear acting on the tiles in a cyclic fashion eventually cause the rubber to fatigue. The damage in this center photo took roughly 3 years to occur. So, the lagging was on there for 3 years, but on this size pulley, the bearings would have been expected to last a lot longer than 5 years. So, it's a very large pulley, and it's having to be removed because of the lagging. The photo on the right shows a failure that appeared in a much shorter time frame and was due to very high shear forces along the edges of the belt. This type of failure typically requires a lagging select analysis to determine what's causing it and then what can be done to try and avoid it. The next lagging failure type we'll look at is wear. Pulley on the left and the pulley on the right both have rubber lagging, while the center photo has ceramic lagging that has worn through. It's not something you see very often, but does happen. Options for improving the performance where wear is a problem include using a more abrasion resistant material, increasing the lagging thickness and the wear material thickness. So for example, you could use thicker ceramic tiles and an overall thicker lagging, or going to a lagging that's more slippery. That's particularly where you have the localized wear. So something like a polyurethane will help there. The next failure mode we'll look at is tile breakage. And this occurs when you get material trapped between the belt and the pulley shell. In some operations, this is very difficult to avoid, but there are a number of things that you can do to minimize the chance of getting tile breakage. Breakage of tiles is made worse when you have low hardness tiles. When you're manufacturing ceramic lagging, 80% of the cost of the ceramic lagging, the materials, is in the tiles. So if somebody wants to make a low-cost ceramic lagging, you buy a low-cost tile. And the tiles don't look any different. They look visually, they look exactly the same. So, you know, a typical 20 by 20 by 5 mil dimpled tile, you can buy those for as low as 2 cents US. And when you buy them for that sort of price, typically, if you measured the Vickers hardness on it, it would be probably down around 600. Good quality ceramic tiles should be above 950 Vickers and will typically cost you around 5 cents at that hardness. A Vickers hardness testing station is an essential tool for anybody using tiles for making lagging, because if you negotiate with somebody, you know, a tile supplier, and you're negotiating based on price, and you don't have the ability to measure the hardness of the tiles, chances are you will end up getting soft tiles. And soft tiles are much easier to break and much easier for the dimples to come off. If you ever look at ceramic lagging and all the dimples are gone, it's probably because somebody's been using tiles with a low hardness. Now, there are some things that we can do to resist the breakage or cracking of tiles. And tile thickness is a way of increasing the resistance to breakage. We use a machine called a flex crack tester, which measures the force to break a tile. If you look at this photo here, this is the flex crack tester. The way it works is the tile is loaded in a jig so that the tile is supported on 2 edges, and then a plunger comes down and applies a load to the center of the tile until the tile actually breaks. Now, for a 5 mil ceramic tile, that's the common tiles that are used in drive lagging, a 950 Vickers hardness tile typically will break between 2,000 and 3,000 newtons. When you put in a 10 millimeter tile, our machine maxes out at 10,000 newtons, so we can't break the 10mm tiles. So effectively doubling the tile thickness, you've got a 3 to 4-fold increase in resistance to breakage. And you can also use even thicker tiles again, 15mm tiles. Needless to say, we haven't tried to measure those. So if you've got an application where tile breakage is a real problem, going to thicker tiles, you'll also need a thicker backing, rubber backing, to help cushion the tiles. So moving up the thickness of the lagging thickness of the tiles will greatly reduce the problem of tile cracking. The last thing that has an impact on tile breakage is when the tiles are contacting each other. You'll see some lagging designs where the ceramic tiles are hard up against each other. When you get material trapped between the belt and the lagging, you get high point loads on the tiles. Ceramics are inherently brittle. When they've got nowhere to move, so they've got a hard tile on either side of them, and no room for movement, it just makes it much easier for them to crack. Putting a layer of rubber in between the tiles, as shown in this photo, helps to protect the tiles from some of these shock loads. And another advantage of having the rubber in between is that you now also bond to the sides of the tiles, and that increases the bonded surface area by about 80%. So putting rubber in between the tiles improves the resistance to breaking, and also increases the bonded surface area. Next thing we'll look at is lagging fatigue. I won't spend too much time on this because we covered it in detail in course 2. But this occurs when the cyclic shear forces from the transfer of power exceed the capacity of the lagging. To improve the performance in this case, we use the lagging select tool. We did cover this example previously. The tool on the left here shows that this is the operating line for the conveyor, operating in an unsafe zone below the tread root, and as a result the diamonds have been torn off. Here the operating line is sort of in the safe zone and on the edge of the unsafe zone. This is for herringbone lagging. So this was a way that the tool was used to improve the performance of lagging on an existing conveyor. The last thing that we will look at is spare pulleys. Lagging selection for spare pulleys. Often a spare pulley will be used to cover more than one location. This diagram is for a large gearless drive conveyor operating in Peru. The pulleys are split into 3 groups. We have the drive pulleys, which is number 4, number 5. We have the high tension non-drive pulleys, which is the head pulley, number 2, and the high tension bend, which is number 3. And then we have the low tension non-drive pulleys, which is numbers 6, 7, 8, 9, and 1. The 2 drive pulleys, the lagging is the same. So the spare would have the same lagging. It's 25mm hot vulcanized ceramic. For the high tension non-drives, which is the head and the high tension bend, the head pulley is contacting the clean side of the belt. So good quality rubber lagging would work well there. The high tension bend, though, is contacting the dirty side of the belt, which means that it has to deal with the belt wear, and it's a very severe, very difficult application. So if you're choosing lagging for the spare, you would put the same lagging as you are getting the best performance on for the high tension bend. That way, if you put it in the head position, it'll work really, really well. For the low tension pulleys, we've got a mixture of dirty side contact, pulleys 6, 7 and 8, and clean side pulleys 9 and 1. The clean side pulleys would work well with just a straight rubber lagging, but the dirty side pulleys would benefit from having something that's more abrasion resistant and more resistant to build up, like a polyurethane. So if I was selecting lagging for the spares, I'd be going for lagging for the dirty side, the more difficult side, which would be something like the polyurethane or the extreme rubber. That's pretty much all I've got for today. Next course in 4 weeks' time, we'll be looking at specifying pulley lagging, what's important for performance. We'll look at performance requirements, physical properties, what properties are important, bonding systems, adhesion requirements and testing, application procedures and records, and warranties. So I guess that's all I've got. If there's any questions, we can go through those now. So there's one question in the chat from Ben. He says, earlier you mentioned pulley wear due to a turnover belt. How do you recommend avoiding this issue? Thanks for the question, Ben. Those particular photos were from a pulley or a conveyor in Brazil, an iron ore conveyor, and it was a turnover conveyor. The rubber lagging on the non-drives was getting that localized wear and was requiring replacement in roughly 3 months. What we did there was we put polyurethane lagging on those pulleys, and the service life went out to more than 3 years. I think the main reason for that was that localized wear was because there was residual tension in the belt, putting shear stresses onto one side. Once the polyurethane lagging was in there, because it's more slippery, rubber on rubber tends to grip, whereas rubber on polyurethane, the belt slides more easily on the lagging. So a combination of the fact that the belt could slide and release those localized shear stresses, plus the improved abrasion resistance of the polyurethane, gave a greatly increased service life. Mark's asked, regarding performance data, do you have good comparable data for FRAS rated PU, HV, rubber, etc.? Mark, are you talking about the physical properties or in-use performance? In use, okay. Not as a comparison. We can probably give you locations where those different types of lagging have been used and the service life that's been achieved. We can probably do that. But I don't have anything that I can share with you at the moment. James has asked, with regards to bonding failure analysis, what is the root cause that is most common with coal bonding? Coal bonding, it's very difficult to work out exactly what causes coal bonding. Coal bonding's such a, there's so many things that can create problems. If you're doing an on-site cold bonding. It can be the cleanliness, the temperature, the humidity, the training of the operator. I couldn't put it down to one particular thing, James, just to say that it's the least robust bonding system when you compare it to hot vulcanizing and cold and direct bond. Emmanuel's asked, is it allowed to add running water when the pulley is sliding even after the belt has reached the maximum tension? Is it allowed to add running water when the pulley is sliding even after the belt has reached maximum tension? I'm not sure what you're referring to, Emmanuel. If there's slippage between the pulley and the belt, if that's what you mean, I would not be putting water on. Water is only going to make the slippage worse. Is that what you're referring to, Emmanuel, or is it something different? Sorry, just say that again.
Am I audible? Are you able to hear me?
Sorry, mate, I didn't come through. Say that again.
Are you able to hear me?
Okay. Mark's asked, does the lagging selector tool have data sets for various FRAS laggings or only non-FRAS? Mark, we've just done a whole series of friction tests with Tunra, and the FRAS lagging is part of that. So that's in the process of being added to the tool. I don't think it's in the tool at the moment, but we can come back and let you know once the FRAS option is in the tool. It won't be far away. All right. Any other questions? Oh, Dion, sorry, I missed one here that Dion had asked. Are the tiles okay to be touching on a direct bond ceramic lagged pulley, or would they benefit from a gap and grout or just a stiffer pulley shell? Dion, usually when we do the direct bond lagging, there's a gap of between 1 and 2 millimeters between the tiles, and that gap is filled with epoxy. Now, epoxy is much stiffer and harder than rubber, so you're not getting the cushioning effect that you get when you have tiles molded into rubber. But I would prefer, if I was doing direct bond, I would prefer to have epoxy between the tiles. And I guess probably the main reason, more so than the tiles touching, is the fact that you get to bond the tiles on both the back and the sides. So yes, I would always have a gap between tiles and direct bond lagging. As far as you've asked about the stiffer pulley shell, normally with direct bond, you do have to consider the flexing of the shell. So a stiffer pulley shell does help. We haven't had any problems with small tiles, 20 by 20, in terms of them coming off pulley shell, but the bigger tiles, some companies use 100 mil by 25 mil tile, a big long tile, and we certainly have seen problems with those popping off. Okay, all right. Well, if there's no more questions, we'll call it for a day. And I hope to see you next session in about 4 weeks' time.